Hello again, welcome back. Let's pick up where we left off. So last time we established the following Lishnarovich type formula for the square of this Dirac operator on the SL2C bundle on our space-like hypersurface inside of Lorentzian manifold N, using the connection that came from N, which I'm denoting with bar. Everything with bar or an H means that it comes from N. Okay, I mentioned something last time about this being adjoint to, to something like a Laplacian, something like a nabla star nabla, where this nabla star is the adjoint to nabla with respect to some inner product. Now let's get a little bit more specific about that. And actually, the inner product that we're going to be interested in has the property that the sum of these two things that I've highlighted in orange together will be nabla star nabla for our nabla bar. But okay, so let's talk about the connection. Or sorry, the inner products. Okay, so I want to talk about how to take inner products of two spinors, two elements of S. Well, for being a nice complex representation, of SL2C, we get a Hermitian inner product that I'll denote with rounded brackets that respects the Clifford multiplication. Yeah. Now from this, we can get another Hermitian inner product, which is actually definite. The one with rounded brackets is not. And I'll denote this one with the square bracket or the pointy brackets, and this is the one that we will be using because we want we want to work with the inner product that's definite, that gives us norms and things like that. Okay, and we get it from the old one by just doing first Clifford multiplied by the time-like vector E naught on the first entry. We want to figure out what is the adjoint with respect to this guy of nabla bar. Okay, so warm-up calculation. So we have this here. So let's take the nabla bar of E naught acting on a spinor phi. Okay, so first of all, it can act on E naught. That gives us part of the second fundamental form, Kij times EI acting on phi. Talked about that last time. And then, the other part, E naught acting on nabla bar acting on phi. Okay, so let's now take the, let's take the derivative of the inner product of two things. So on one hand, and by the way, so the original Hermitian inner product, that's the one that is respected by nabla bar, which is the connection that we're using. The pointed brackets one, that is respected by the Riemannian connection on M. So if we want to use the, get the connection involved in the product rule like this, when we take a derivative like this, we need to first convert to the rounded one, the one that respects the nabla bar. Okay, so you first convert to that. I'll just point with the laser pointer here. Then, do usual product rule, use the formula we just found for the second, involving second fundamental form, and then E naught acting on nabla bar, acting on phi, paired with psi. Now the second term is simple. That is just this new inner product of what you would expect. The other one is a little bit more interesting. So to get, we need to make E naught appear in order to convert back into the pointed brackets. Okay, so what is the adjoint of nabla bar? Well, it is this operator here, the one that appears in the acting on the left hand, the other part of the pairing. That is the formal L2 adjoint of nabla bar with respect to this pointed brackets inner product. So that's this right here. So nabla bar star with respect to the pointed brackets is nabla bar because of that with a minus sign. And then the second fundamental form term. So these two things in the orange in our Lishnarovich formula, they combine to be, I'll write that down here. These two things combine to be nabla bar star. I'll put a circle around the star just to make sure to make it clear that this is the one with respect to the pointed brackets. Okay, so these things add up to be the real Laplacian that works well with the pointed bracket inner product. Okay, because we're going to be gearing up for using we're integrating this formula by parts. After pairing using the pointed brackets, we'll need this. Okay, also one more remark before we move on. The curvature, we need to understand the dominant energy condition. Okay, so remember the tensor T from before. Actually, I guess we were calling that 8 pi t. That acts on a spinor according to the following. So it was just Ricci, and then minus 1/2 scalar curvature times the Lorentz metric, E alpha, E beta, psi. That's how it is, 2 tensor x on psi. So if you just look at the T00 plus T0I, or E0, EI acting on psi, that is just written as the following. Okay, we're now from the T00 part, you get Ricci 00, and then plus, because h of E0 is -1, so that changes the +1 to, or that -1 to a +1, the scalar curvature. And then just from the T0I, well, when you plug in 0 and I goes from 1 to 3, the metric term vanishes because EI is orthogonal to E0. You just get these Ricci terms. Okay, so let's go back up to the curvature term we see here. I'll call that R, curly R, by the way, acting on psi. That is, well, twice what we just wrote. It's twice this thing. And so if we calculate that and use Cauchy-Schwarz, this thing, yeah, so on one hand, it looks like just T00 norm psi squared, and then plus T0, psi, and then T0I, E0, EI, psi. And this is, of course, greater than or equal to T00 psi squared plus, well, minus the norm of this vector, T0I. That vector is I ranges from 0 to, or 1 to 3 squared times, or not squared, just the first power, times phi squared, which is greater than or equal to 0 by the dominant energy condition. That's exactly the dominant energy condition, that this difference here is non-negative. Okay, good. So this term here is morally a positive thing, non-negative thing, and it definitely, when you pair it with psi, it's literally, that's a pointwise non-negative expression. All right, now let's approach the proof of the positive mass theorem. All right, so now let's fix our setting again, just to make sure where we are. So we have an initial data set, MGK, asymptotically flat. So G is decaying to the flat metric, and its derivatives are, and its second derivatives are, decaying to the first and second derivatives of flat metric, just to say 0, according to this rate, and we satisfy the dominant energy condition. We have one and say we're complete. So no boundary in this setting, just one end. Let's fix this setting. And this is Witten made use of this implicitly, and Parker-Taubes gave a more general, rigorous proof of this theorem. Okay, so fix some what I would call constant spinor, or what people, I'm not the only one, what people call constant spinor. Because it's just an element of the vector space. By the way, remember on R3 minus a ball, there is one and only one spin structure, and it's got to be the trivial one. So the spinor bundle over here, this is really just our, when you restrict the spinor bundle to the asymptotically flat end, M minus that compact set, which is diffeomorphic to R3 minus a ball, here it's isomorphic to just the product of the base times the spinor bundle S. So that allows you to think of just an element of the vector space as a spinor on the asymptotically flat end. Okay, so it's just the element of the vector space, but we're thinking of it as a spinor field defined on the end of our asymptotically flat manifold. You can extend it to a global section by just partition of unity, killing it off before you get to the interior of the manifold. By interior of the manifold, I mean that compact set you need to remove in order to be diffeomorphic to R3 minus a ball. All right. So here's the statement. There is a unique spinor on your asymptotically flat manifold, your initial data set, satisfying, okay, it's Dirac harmonic, in the sense that it's in the kernel of the Dirac-Witten Laplacian, or Dirac-Witten operator, and it converges to psi naught. Again, psi naught we're thinking of as a spinor on our manifold, in the sense that the norm goes to 0 as x, the radius goes to infinity, using the asymptotically flat coordinates on the end of your manifold. So as you move out to infinity on R3 minus a ball, this norm goes to 0. And also some other conditions. I'm not stating this in the full generality. They prove something stronger, but I refer you to their survey and their paper for this, these more detailed statements. But also the gradient of psi goes to 0 as well. Okay, how do you prove such a theorem? I'm not going to tell you really, but I'll just sketch. And also, I want to point out that they require the dominant energy condition. Well, why is this? Well, so the strategy for solving something like this is, okay, you extend this phi naught to phi 1, some section of the spinor bundle on the whole manifold, which is so that so it's 0 in a compact set. So consider phi1, it agrees with the constant spinor on R3 minus a ball, and it's some globally defined object. Then you want to try to solve. So, we look for some phi hat, let's call it psi hat, so that the Dirac-Witten operator on psi hat plus psi1 is 0. Okay, so in other words, this is going to be the object. That's the spinor that you want, or that's the harmonic spinor that you want. And the equation that you would want to solve is this is equal to minus Dirac acting on phi1, which is hopefully small. I mean, it should be small since phi1, it's literally the constant spinor at infinity, and your manifold is getting rather close to, it's converging to flat space as you go farther out in the manifolds. It's asymptotically flat. And since the constant spinor at infinity, it's harmonic with respect to this operator on flat space. It's a constant spinor, so it's trivially harmonic with respect to the Dirac operator on R3 from the standard metric and everything. So you should, everything's a perturbation of that, so you should expect this to be small. It will be small, depending on how fast the manifold converges to flat space. Okay, so this thing goes to 0 very quickly. Okay, so you want to solve an equation like this. This is what you want to solve. You think of the right-hand side as some given thing, and you are seeking a psi hat so that it solves this equation, this Poisson equation. This psi hat, you would expect to, you would want this to go to 0 as you go to infinity, or you want it to go to 0 as you go to infinity, since you want the resulting thing to be asymptotic to this psi1. So that's the coupled system you want to solve, this one with these asymptotics. When you integrate by parts, the boundary terms for such a spinor would go to 0. Only if they don't go to 0 will you get something in the boundary terms. Anyways, the point is you get something like this plus psi, and then the curvature term in the Lishnarovich formula here, integrated over m. Okay, so this gives you like an upper bound for your operator in a sense. And also notice that if you have something in the kernel of Dirac bar that goes to 0 like this, well, the right-hand side is non-negative, as we just mentioned, by dominant energy condition, tells you that's non-negative. So both terms would have to vanish, which means that that harmonic spinor would be parallel, and your geometry is much more simple. As we'll discuss later, I actually have to be Ricci flat, or some connection on you has to be Ricci flat. Anyway, so this gives you an idea that this Dirac bar on spinors that go to 0 is kind of bounded above and below, and can be inverted. That's the rough idea of the argument. Details in this Barker-Taub's appendix. Okay, so now let us, that was just a brief aside. Now let us approach the proof of the positive mass theorem. Okay, so we'll fix the spinor at infinity psi naught and work with one of these guys from the theorem. So let phi be as above here. And so we have our asymptotically flat manifold complete. And now we will take the interior of coordinate spheres, SR. We have a chart to R3 minus a ball that allows you to transport these coordinate spheres to the manifold. And let's call MR the inside here. It's well defined because spheres, they separate Euclidean space into one of two components. So it's the same thing here. Okay, so let's integrate over MR, and then we'll see what the boundary term is, and then we'll take, when we integrate by parts, and then we'll take this SR as R goes to infinity, and that will allow us to conclude the positive mass theorem. Okay, so what follows will be a heuristic calculation. One should be much more careful, and again, I'll refer you to the Parker-Taubes paper and subsequent papers, the bibliography. One should be rather careful about the asymptotics of the spinor, which I've been a little bit lazy about, and when you do this integration by parts, you have to take some care here. So I'll gloss over a lot of those things and give you a moral calculation of the integration by parts formula, which is we'll get the same formula. It will be maybe slightly less precise. Okay, so what do? Well, we take this. We take the pairing of Dirac bar, phi or psi with psi, using the pointed brackets inner product. All right, well, this is obviously 0 since we chose this to be Dirac harmonic. So when the Lichtenevich formula, on one hand, we get this when we integrate by parts off one derivative. So the only thing that's left in this, let's review the formula again. So the left-hand side here is 0. This is just together here, it's the adjoint of, so this thing here is phi nabla bar adjoint nabla bar psi, and so this is just equal to nabla bar psi nabla bar psi. And so this is the, that's where this comes from, and that is the curvature term. All right, and the boundary term is, roughly speaking, the normal derivative of psi, but when you make that precise, we get the following here. So you have EI, EJ acting on nabla bar J psi, and then times, what's basically the dual of one form EI here. When you take that on the sphere, it just becomes nu I times the volume form on the, or the area form on the sphere. Okay, so let's note a couple of things. All right, so the left-hand side, definitely non-negative. This is a norm of something plus that curvature term, which we already agreed was non-negative. Okay, so also let us compute what nabla bar, we want to compute this, this boundary term. That is the whole goal at this point. Identify the boundary term with mass, hopefully. Okay, notice this is just like a bunch of derivatives of psi. Psi is going to a constant. So the literal derivatives of psi are going to 0. But we're integrating on something large. So we're integrating something that's going to 0 over something that's very large. So we have to be a little bit delicate here. We want to write this carefully. Okay, so nabla bar J psi naught. This will, the difference between the psi and the psi naught in this rule goes to 0. Again, a little bit vague about the details there, but this is morally what happens. And so let's try to understand what is nabla bar j acting on psi naught. Well, it should be 0. It's the first derivative. But then you remember we have Christoffel symbols. And that is basically all that we have in this covariant derivative here. Okay, so this splits up in terms of the connection in terms of from the Levi-Civita connection of mg, and then minus the second fundamental form term, which takes this form as we worked out in the last lecture. And now the nabla j, the connection from mg, splits into two pieces. So we have a little literal, partial derivative rate of change of psi naught, which goes to 0 because it's just a constant. And then we're left with this Christoffel symbol. And you know how this is the Christoffel symbol that comes from vector fields, the one that we're used to, the one given down here. And then to translate that in terms of acting on psi naught, to multiply by this Clifford multiplication and a factor of a half, because again, two forms act on spinors by 1/2 Clifford multiplication. Okay, so now we want to analyze these two terms. All right, and just to remind you what the Christoffel symbol looks like in terms of the metric tensor. Because again, the mass formula was in terms of the metric tensor and the second fundamental form. Those integrals on spheres of infinity. Okay, so combining 1, 2, and the boundary form together, we have these two terms. One from the Christoffel symbols here, a product of 4 actions by Clifford multiplication, tied up with different components of the normal vector or different parts of the area form, however you want to think about it. And then a triple sum over here. These are all going from 1 to 3 of the second fundamental form stuff. And we have an E naught here because that's how the second fundamental form is acting. These two. This stuff is that part of the second fundamental form up there. Okay, and we had a minus sign from integrating by parts, but both of these terms in the boundary from integration by parts have a minus sign, so we get a plus out in front. All right, so now how do you work out what goes on at this point? All right, so the punchline is A is going to be converging to the, as R goes to infinity, the term coming from A will be the energy, and the term coming from B will be a part of the linear momentum, the total linear momentum. Okay, so let me just give you an idea about how to do this sort of calculation. I won't do it in the 100% details. How do you get to the desired outcome? Well, you'll run into you'll find yourself adding up a bunch of terms like this, and if you write down these Christoffel symbols in terms of the metric, you'll have this going on in the terms that you encounter. You'll have a 1 indice here, and then repeated in 2 and 3, and the repeated indices in 1 and 3. And the difference of 2 Christoffel symbols like that will just be a difference of two first order terms in the metric, like this: GJA derivative in A direction minus GAA derivative in J direction. And this summed over A, times nu J summed over J, that is the thing that you integrate over spheres. Take the limit as the sphere goes to infinity, and that becomes the mass. Okay, the other thing that you need to use in order to calculate or complete this calculation is the following. If you ever run into a term like this, well, that becomes the following. So if you do a Clifford multiplication by EI, you pick up a minus sign, you get an EI here. If you do Clifford multiplication by EJ, that allows you to, at the cost of a sign, move a J from one side to the other. And now if you then do a switcheroo of EI and EJ, you know, because I'm assuming that EI and EJ are different, then you pick up a minus sign just from the anti-commutativity of these things. And then if you change the order, I forgot a bar here, if you change the order of the Hermitian inner product, you pick up a conjugate. So what do you find? You find that the sum of this with its conjugate is 0. You just add that to both sides of this chain of inequalities here. And so what can you say about a number whose, so that when you, a complex number, so that when you add it to its conjugate, you get 0. Well, that means that the real part is vanishing. So the real part of a term like this vanishes. Now, we know that the left-hand side of this whole integration is real. You know, that was the point of using the pointy bracket thing, is that it norms of things are real. So this here, yeah, so terms like this will vanish since they're imaginary and you know they won't appear. Okay, so anyway, so after you use these those calculational tools, you'll find the following. Okay, so A, we got a 1/4 from that Christoffel symbol. Integral on the boundary of MR, this SR. You will get the norm of psi naught times the correct partial derivatives that, and this is a D area form, that gives you the energy. This thing will converge to, I guess, 4 pi, the energy, as R goes to infinity. The other term, B, is a little more simple, but it will converge to this, which is a little bit more complicated. The Clifford multiplication doesn't go away entirely. You still have a E naught EA acting on the spinor. Here, this is the trace of K. This is just the 8th part of Ki. And this whole thing here, so if you call PA this quantity, the sum over just I, just don't sum over A, but just this same quantity where you just sum over I, this is the thing that when you integrate PA over SR, this goes to also 4 pi, the total PA, you know, ADM PA of the initial data set, DA. Okay, so what we have here is kind of a projection, you know, as I wrote it here, this is kind of like a projection of phi naught onto that part. You're doing a Clifford multiplication of the integrands of the thing that gives you the total ADM momentum in the A direction, but consider it as a vector. A ranges over 1, 2, and 3. Clifford multiplying, you know, acting on the psi naught. Okay, so in the end, what do we arrive at? We get the following. Here's, so this should be kind of in quotation marks. This is still being integrated over MR, taking the limit as R goes to infinity here. You know, yeah. dA. Okay, so the sum of these two things, as we take the limit as R goes to infinity, will be 4 pi energy times the norm of that constant spinor. We're still free to choose the constant spinor. We haven't done that yet. Plus this kind of projection of psi naught onto the part of, onto the total well, onto the integrand that will eventually give us the total momentum in the a direction. That vector as you range a over 1 to 3. Okay, so we're free to choose the psi naught. In fact, we can choose it so that this term here becomes just minus PA times the norm of psi naught squared. There's, in fact, many choices of psi naught that would allow you to conclude this, to identify that boundary term with the, this is minus the norm of PA. Consider it as a vector. A is ranging over 1 to 3. Okay. So that gives the theorem. So for an appropriate choice of the constant spinor at infinity, you find that the gradient, with respect to the nabla bar squared plus that curvature term, which is non-negative point-wise, we already established that, is equal to 4 pi e minus norm p, which is exactly, we know this is non-negative. So that tells you, in particular, if you have the dominant energy condition, then E minus norm P is greater than or equal to 0. Or in other words, the total energy momentum is time-like or non-space-like, which is the, that's the main theorem. That's the main positivity. Now, notice there should also be an equality statement. If this quantity vanishes, then you should be able to identify what's going on. That should be a rigid situation. Basically, you should arise mgk. If the total mass vanishes at an end of your asymptotically flat manifold, then your initial data set should arise as a, from a graph in Minkowski. That whole issue is a little bit delicate. Let me just say that what we can see from this point is something, still very simple and beautiful. If we are in the time symmetric case, say k identically vanishes, the second fundamental form k vanishes. Okay, so then we're in the scalar non-negative setting, of the manifold M. That's the dominant energy condition. And it says in the integration by parts formula we just found is that the total energy is bounded below by the square norm of the gradient of the harmonic spinor. Very, very nice statement. Also plus the scalar, 1/4 the scalar curvature of our Riemannian manifold times the norm of our spinor squared. Okay, anyway, but the very nice clean statement here in the Riemannian setting where k vanishes. And you can see if the energy vanishes, well, then your scalar flat, first of all, because this business has to vanish. And you have a parallel spinor. Nabla bar of the spinor has to vanish. And so we have special holonomy. I mean, that is very restrictive for the curvature of a manifold if it has a parallel spinor. So in particular, you have to be Ricci flat. And it turns out if you're Ricci flat and asymptotically flat, you have to be flat. You could kind of think of that as like some kind of version of elliptic regularity for the curvature tensor. But you could establish that with the Bishop-Gromov volume comparison or a number of different tools. But yeah, Ricci flat plus asymptotically flat will tell you that you're flat. Certainly in this, yeah, that doesn't even need to be that complicated, but we'll leave it at that. So you get this rigidity statement that if you're in the time symmetric case, if the energy vanishes, then your manifold is Euclidean space, topologically and geometrically Euclidean space. The t equals 0 slice of Minkowski. Okay, so that's the positive mass theorem due to Witten and exposited by Parker-Taubes. So in the next lecture, we'll see another perspective on this positive mass theorem. Okay, thank you.